Welcome back, students. In the previous video, we were talking about electric dipoles. We said an electric dipole is a unit that has both positive and negative charges of equal magnitude but of a different type. They are also separated by a very small or short distance. And we also talked about why it was important for us to study things like that, because we said water is a natural dipole. It's a permanent dipole because the dipole nature of water will not go away. Okay, so it's a permanent dipole too. And then we also said that all the other elements that you see in nature can be converted into a dipole by applying an electric field. So that way, kind of, if you make one charge move slightly towards the field and the other charge to move slightly away from the field. So the charge centers do not exactly coincide. So there is this little separation. So all elements can act as a dipole. So that is also we discussed yesterday. And then we went ahead and then found the field due to an electric dipole along its axis. We take a point on the axis, and we also found E at any point along the axis. We found a couple of things there. One is that the field, the electric field due to the dipole along its axis, always in the direction of the dipole moment, P. If P is like this, from here to here, then the electric field was also in the same direction, whether you take this side or this side. So we did that too. I want to talk about a couple of things about the dipole and the electric field due to the dipole at a point on its axis. So the first thing is, we will talk about the unit for dipole, right? Dipole moment. So we said the dipole moment is P, okay, and that the magnitude of that was Q into D. That was my definition of it, but the textbook definition is Q into 2A, so 2AQ, 2A for D. So 2AQ is the dipole moment. I mean, where A is half the distance between the two charges. So like if I have a positive charge here, plus Q here, and then minus Q here, then I called the whole thing as D. But then if we take the center of the dipole, which is O, let's say, then this is A, and this is A, the D is equal to 2A, so 2A. So this is what we said. Then what would be the unit for the dipole moment? The unit for the dipole moment is simply Coulomb meter. With you have to take the charge and multiply it with the distance. So it's Coulomb meter. That's a unit for dipole moment. So the unit for dipole moment is Coulomb meter. Okay, that's the unit for it. That is one point about this. What is the second point? The second point was this. Well, when we calculated the field along the axis of the dipole, do this way. Suppose I take a point here, A, and then I calculated the field along the axis of the dipole, and here, any point, doesn't matter. The point is along the axis. Then we said that the electric field due to the dipole was equal to 2P vector by 4 pi epsilon naught into RQ. Okay. This is what we got. You may think that the unit of this will not match with the unit of the electric field, the definition that we had before. So what did we have when we took a point charge? So when we took a point charge, for a point charge, what was E? E was given by Q by 4 pi epsilon naught into r square. Right? So this is what we saw. It's Coulomb's law. Q into 1 into 4 pi epsilon naught r square. That's what we saw. So it is r squared here, but you got r cubed here. So does it mean that the unit for this has changed? I hope you follow the discussion. You have q by 4 pi epsilon naught r square here, but here you have p by 4 pi epsilon naught r cube here. But we say this is electric field and this is also an electric field. So does it mean that you have r squared here, you have r cube here? Does it mean that the unit has changed? And if the unit changes, how can these two quantities be the same? One will be apple, another one will be orange, and how can you compare them? Okay. No, the unit doesn't change. So the extra r here, okay, the extra distance, that meter that you're bringing in here, is compensated by the meter here. So what is P basically? So P is actually, let me try the unit for this. What is this? The P is actually Coulomb meter, right? And what we're going to have here, and this is going to be meter cube. We just consider this alone, these two parts. No? I'm not worried about the epsilon up there. Let's not worry about it right now, because it's going to remain the same for both of them. What is different is only this part, q by r square and p by r cube. But p is Coulomb meter and r cube is meter cube, so 1 meter will cancel with the meter cube. So you will effectively have Coulomb per meter square here. Same you have here too. Coulomb per meter square. So effectively, even though you say that this is r cube, because you have p here, which has a unit of Coulomb meter, the meter in the numerator will cancel with one of the meters in the denominator. Then you are going to effectively have Coulomb per meter square for p by r cube, just like q by r square. Okay. The only difference here is this. This meter is a separation. Okay, there is no such meter here. It's just d by r cube. It's like this, right? Effectively, if we say this is going to be 2 p is qd, right? 2 qd by 4 pi epsilon naught r cube. Okay. So you have d and r here, d by r, but not r by r. You won't exactly cancel. It's a very small number, it's a big number, but the units only will get cancelled. But this value is different from this one. It's a small value, it's a big value. Okay. So that is how we can explain this. The point here is that because you have an r cube in the denominator, the unit of E will not change. The unit will be the same as this E. The reason is you got P there, not Q. But P will comprise of both Q and D. There is a meter here. And there is an extra meter here. That meter and this meter will cancel. So the unit will remain the same. The unit is for E here is also going to be Newton per Coulomb. Newton per Coulomb only. Just like that. Yes, and that's the point I was trying to make. So there are 2 points. One is the unit for P, the dipole moment, electric dipole moment, and then the unit for E. Okay. So now let's move on to do a derivation for the other part. Remember, we talked about 2 things yesterday. One is electric field along the axial line, and the other thing was electric field along a point on the equatorial plane. Right? Okay. So it's like this now. So it's the second part. I'm going to do the second part now. So E due to a dipole at a point on the equatorial plane. equatorial plane. Yeah. So it's like this, right? Suppose I explained it to you in the previous video itself. Let me explain that again. Yeah. Suppose I have the dipole like this. This is a dipole. Yeah. Let's say this is the positive part. This is the negative part. Okay. Suppose I have the dipole here, and equatorial means the center. You know, the equator, right? Where is the equator? So it goes along the center of the Earth. Okay. Likewise, the equatorial. When I say the equatorial plane, that plane must go through the center like this. Okay. And if I were to look at it in this angle, so how it's going to look? So it's like this, right? Okay. So let's say this is a plane, and then the dipole will go like this, through this, right? Imagine the other half is the other side. So one half is here, the other half is there. So now if I take a point here, let's say this is how the dipole goes in. Dipole goes in like that, and if I take a point there, you see that point is going to be at a distance r from here, from the dipole. Okay. Now, so let's say obviously you are going to bring a unit positive test charge at this point. So this is point A. Okay. So this is the dipole. You have negative charge here, positive charge. This is going to pull it in this direction. It's going to pull it in this direction. And what would the other side do? The other side, if you see, we're talking about this point, right? Talking about this point now. The other side will push it in this direction. So this will pull like this, and that will push up like that. And this unit positive test charge will be pulled down and pushed up like this. So it's going to move towards you. Okay? I hope you understand that part. And that is not true for just this one point on the equatorial plane. Suppose if we take another point along the circle. All the points along the circle will do pretty much the same thing in order to. So here, again, this will pull it in this direction, that will push in this direction, and this will also try to move in this direction. All of them will try to move towards you. Every point on the circle will have an E field towards you now. If this is negative, and that's positive. Okay, so, and they will have the same value, notice, because they're separated by the same distance. Right? Because this is R, this is R, this is R, this is R, same. So if it's 10 centimeters, we do 10 centimeters. So everything will have the same magnitude and direction. Okay. So if I calculate for this one point, I have calculated for all the points on the circle. Right? Because if you calculate E for A, then if this is B, then B will also have the same value as A. And if this is C, C also will have the same value as the A. That is what we are going to do now. Let's do it. So now if we take the dipole again, right? So this is the positive part, plus Q here. And let's say this is minus Q. Minus Q. And this is the distance of separation, D. Or I can say, I can take this as a center, I can call this as point O, and then it's going to be A, and this is going to be A. So D is equal to 2A. We discussed all this before. So now, let's imagine that the equatorial plane is going through this dipole. So this is a dipole, it's like this. The plane must go through the dipole, like this. The plane must go through the dipole, right? So it goes through the dipole. Now I'm going to take a point A. Let's say the point A is here, on this plane. This is A. Okay? So let's see. Now what I'm going to do now is from the center, let us suppose that this is at a distance R. and this is A, right? So this distance is R. From the center, the point is R, from the center of the dipole. And this is the distance of one charge to the center of the dipole, A. Now, let's see what's going to happen. What would be the nature of the field? Well, what is this going to do? It's a positive charge, and you are going to bring a unit positive test charge here. So it's positive, this is positive, there's going to be a repulsion, right? So this charge will repel it. Okay, repel it like this. So that is E A due to the positive charge. Okay, then E of A due to the positive charge is that. Then what will this do? This is going to attract, because this is negative and this is positive, and this will attract. Okay. So this is going to be E A due to the negative charge. So the resultant field will be the sum of these two vectors. I need to vectorially add EA plus and EA minus together. See, I cannot take this one and subtract this. Notice it, like they are not in the same direction. Like, no, it's not, they are not along the same line. Now they are different. Okay, I cannot simply add or subtract. I need to go for a vectorial addition. Right? Okay, so the effect would be, the resultant would be something like this. So this will be the resultant. Maybe I'll use a different color. Hope this works. So that's my E. That's my E. So one thing is for sure, this E is acting in a direction opposite to the direction of the dipole moment. P direction is what? The P direction is from negative charge to the positive charge. So it's acting in this direction. This is direction of P, right? It's the P direction, from negative to positive. But E is in the opposite direction. Okay? So the E direction is minus P direction, opposite to the direction of P. Right? The direction of E is going to be opposite to the direction of P. So that's it. So that's one, that is clear. Second, how do you calculate EA plus? It's simple, right? It's very simple. So how do you do that? First, EA plus. What's the magnitude of that? It's going to be, say, K. I'm not going to use 1 by 4 pi epsilon naught. Okay, I'll just use K. So K positive Q, okay, divided by this distance squared. But what is that distance? It is R squared plus A squared, right? Because it's a right angle triangle. So it is A, B, C. So C squared is equal to A squared plus B squared. So that's the formula we use. So this distance, okay, I'll probably do that. Maybe I can call this as C, better, right? So C squared is actually equal to K Q by A squared plus R squared, or R squared plus A squared. Good. And what about this? EA minus. That's what's magnitude. Same thing. So EA minus is also equal to K Q by, this will also be C at length, because like it's, like this point would be equidistant from this point and this point. So because it's going through it's on the center. So again KQ by C squared. But now I'm going to have negative sign. But what does the negative sign mean? The negative sign simply tells you that it's an attractive force, and beyond that it does not have any other significance in this case. So I'll stop. I don't even need it basically, right? The negative sign just tells me that it's attractive. I cannot take this number and subtract it, right? Because they are not acting in the same direction. all the negative sign tells me is that it's an attractive force. That's all it tells me. Okay? And then I need to do this vector addition later, whatever that is. So I don't need the negative sign to calculate the magnitude of this force. So k cube by c squared, and that will give me k cube by saying a squared plus r squared. That's wonderful. Okay, but what's the problem? I need to add the vectorial. So how do we add the vectorial? Maybe if I can find the angle between these two, right? If I can find the angle between these two, then I can do this 2ab cos theta thing. I mean, this vector E is equal to EA vector squared plus EB vector squared plus 2AB cos theta. So I can do that. But do I know it? Do I know that? No, right? I mean, I feel I can make out from here. But a better way of doing that will be to resolve these vectors along the x and the y direction. Suppose if I resolve this vector, note here, this one's like this. Okay? I can say that this vector is a combination of this vector and this vector. This vector plus this vector will give me this. Likewise, this is going to be a combination of this vector and this vector. And note that this vector is cancelled by this vector because they have the same magnitude, and the angles are going to be the same here and here. So we will have the same value here, and get cancelled. It's very easily get cancelled now. Okay? So this part and this part will get cancelled, but to look at this part, this is in this direction, and this is also in this direction, so they will get added up. Right? So if we find this part, and that is actually going to be equal to this part, like symmetry, you can see the symmetry of it. This part is going to be equal to this part, and if we can find this, then twice that would be the length of this vector, right? Fall here, this will also fall here. So this one plus this one will give you this E, right? Okay. Now the question is this: how do I find this? First of all, I can treat this to be theta. If this is theta, then this is E cos theta, EA plus cos theta, right? Okay. So what is this contribution? It's like, okay, I'll redraw it. For example, this vector E A plus, I am doing it like this. This is theta, this plus this. So what do I need? I need this, right? I need this. And what is that? And that is actually E A plus cos theta, for it's up till here. And what about the other part? Then you have this part, right? That is E A minus, and same angle theta is going to be there, and I need this part, and that would again be equal to E A minus then cos theta. Right? E A minus vector cos theta. So that is that. So that will also have this. Okay. But then what is E? What is E? E that you are interested in is equal to this vector plus this vector. So actually E is equal to E A plus cos theta plus E A minus cos theta. Since E A plus and E minus is the same, then I can, this would be the same number, but just has a different name. Okay, so that's all there is to it. Since this magnitude and this magnitude is the same, then I can write it as 2 EA plus cos theta. So that's my E. Okay. Okay, now I've got 2 is a number. I don't have to do anything about it. But what about EA plus? I know EA plus is this number, k cube by a square plus r square. That is taken care of. But what about cos theta? How do I get cos theta now? Well, look at this picture. Look at this picture. It's like this, right? It's like this. So if this is theta, and this should also be theta. From basic geometry, like this. Right? There are parallel lines. If this is theta, this should also be theta. So this is also theta. Now I can find cos theta for this, right? And if I can find cos theta, that's the same cos theta for that. So I can find cos theta from here. So what is that? Cos theta for me, from this triangle, which has the same angle as this, theta 90, similar triangle, right? Theta, and this is 90, this is 90 minus theta. Same here, same theta, 90, 90 minus theta. So this triangle and this triangle are similar triangles. So cos theta can be found, cos theta for this can be found using this triangle now. So cos theta is going to be equal to what? A by C. Okay, so what I'm going to get now? A by C. So A is fine, but what is C then? C will be equal to A squared plus R squared square root. Right? So A by C. And that is also can be written as A by A squared plus R squared, the whole power half. Wonderful. So that is my cos theta part. So I got everything now. I got 2, I got EA plus, I got cos theta. So now I should be able to find E using these pieces. So E now is equal to 2, what is EA plus? K cube by A squared plus R squared. Okay, wonderful. And what is this? Cos theta is actually A by A squared plus R squared power half. So if you combine these two, then what happens? It gives me 2A cube into K, 2A cube into K is divided by A squared plus R squared, the whole power. This is 1, this power is 1, this power is half, just 1.5. When I add these powers, 1 half must be 1.5, which can be written as 3 by 2. Right? So this can be written as 3 by 2. So that's the expression. And what is this 2A cube? 2A cube, you know that it is P. Right? P is 2A cube. So I'm going to write it as K P by R squared plus A squared, the whole power 3 by 2. Okay? K P R squared plus A squared, the whole power 3 by 2. Wonderful. So what am I going to do now? I know the magnitude and I also know the direction. Right? Okay, so before I finally put these two things together, let me make one more adjustment. What is the adjustment? Suppose this R, this distance is much greater than the distance of separation between the charges. Then what happens? whatever we did yesterday. So if R is much greater than A, then I can ignore A squared in this equation. Then A squared can be ignored when compared with R squared. R itself is greater than A, much greater than A. Then R squared must be much greater than A squared. We saw that yesterday. We took 1000 and then 1, and 1000 became 1 million and 1 was 1. So 1 million and 1 was a much smaller number, so I can simply ignore it. So this becomes, E becomes what? Now E becomes Kp by A squared can be ignored, so that's going to leave me just R squared power 3 by 2. Then this 2 and this 2 will get cancelled, so I'm going to have Kp by R cube. And if I expand it further, then K 1 by 4 pi epsilon naught for K, and then P by R cube. So that's the magnitude. So E is equal to 1 by 4 pi epsilon naught into P by R cube is the magnitude. Then what's the direction? So the direction is actually in the direction opposite to P. Okay? P is in this direction, but E is in that direction. So the direction of the field is opposite to the direction of P, the electric dipole moment. So if we incorporate everything here, and what I'm going to get now, it's going to be E vector is going to be equal to 1 by 4 pi epsilon naught, then P vector by R cube, alright, but then direction opposite to that, so I'm going to have minus here. Okay, so that is the expression. Okay, so this is a minus here. Okay. That is E vector. So, if you compare what we found for the electric field due to the dipole along its axis, what did you find? In the previous video, we said if you have a dipole here, plus Q, then minus Q, and if you take a point along the axis either here or here, then E here, okay, E was in this direction, in the same direction as P, this is the direction of P, was there. And then the magnitude of this was E was equal to 1 by 4 pi epsilon naught and 2P by R cube. So this is what we did in the previous video. In this video, you got E is equal to 1 by 4 pi epsilon naught P by R cube, but in the opposite direction. You see, this E for the same distance as R. The same distance, we take this distance, same distance R, take this distance R. For both these cases, this E will only be half this E. Okay. Half the value is, you see 2P, but only P here. And it will also be in the direction opposite to the direction of P. So along the axis, let's say, if this is the charge, along the axis, at a particular distance, say 10 centimeter or 1 meter or whatever, you will have a certain value of E at that distance and in this direction. This is positive, this is negative, so P is in this direction. So E will also be in this direction along the axis. But at the same distance on the equatorial plane, any point you take, same distance here, equatorial plane, this E value will be half of that E value and will also be in the opposite direction. So you will see here every point will be coming towards you. These arrows will be coming towards you. Okay. But then they also will have after current for the same distance here along the axis. So that is what you need to understand from this. And you note that the field falls by 1 by r cube. So it will fall quickly, much quickly, quicker than a point charge. If you take a point charge, how much does it fall? Like it is inversely proportional to r squared. But here it is inversely proportional to r cube. Doesn't mean that the unit changes. Notice, because you got already a meter here in P. But that's a constant. This separation is a constant. But if you take this point and this point r can vary. So this field will drop to the third power of r. 1 by r cube is how this field will drop due to the dipole. So the dipole field will drop much quicker than on a single charge. Okay, like it will be the single charge will be 1 by r square. That's the field, right? But for the dipole, it will be 1 by r cube. Is what you got there. Unit doesn't change. And keep that in mind. Even though it falls by 1 by r cube, the unit does not change because you already have a quantity a or d in the numerator. But that's a constant. That doesn't change with distance. Okay, so the unit does not change, but then the value changes much more quickly as you go farther from the dipole. And if you go too far, obviously there will be almost no field. So you see, then this separation is, the dipole will be like this. Let's say, even if I take the dipole to be like this, positive charge and negative charge here, if we go 1 kilometer from here, what would be the field value? 0. Because if you take a point 1 kilometer from here, this distance of separation does not make any sense. It is like they are cancelling each other, very close to each other. So the field due to a dipole at a far away distance will be 0. But in closer distances, it will still have an effective electric field. Okay. And that electric field will fall off much quicker than a single charge. The value of the field will fall faster because you get r cube in the denominator rather than r square in the denominator. Hope this is clear to you. Okay, so now that we have done these two derivations for a dipole, let's try to do the example problem 1.10. Let me read out the problem, then we'll go ahead and do it. Okay. Two charges, plus 10 per microcoulomb and minus 10 per microcoulomb, are placed 5 millimeter apart. Determine the electric field at a point P on the axis of the dipole 15 centimeters away from its center O on the side of the positive charge as shown in figure 1.21a, and B at a point Q 15 centimeters from O on a line passing through O are normal to the axis of the dipole as shown in figure. Okay. So what have they said? They said there are two charges which act as a dipole, because like we're also talking about a very short distance, right? So one is minus 10 microcoulomb. Okay, it's like this. You have, let me take a charge. Okay, this is plus Q and this is minus Q, and the distance is also given. Okay. So what is given? So what is the value of Q? The Q value, this is 10 microcoulomb, 10 into 10 power minus 6 coulomb, and this is actually minus 10 into 10 power minus 6 coulomb. So 10 microcoulomb. And what's the value of D? It's the 5 millimeter apart. So which means it is 0. Actually half a centimeter, right? Like it's 0.5 centimeters. Just give it a blank. 0.5 centimeter. So that's half a centimeter, that's the distance. Then what is said? They want you to find the value of E at a point which is 15 centimeters from the center of this dipole O. This is 15 centimeters. Okay. On the side of the positive charge. Let's say this is A. This is what you need to find. So from the center, this distance is 15 centimeters. Wonderful. Okay. So they want you to find E here. Which means this is a dipole, and compare the distances now. Like this is 15 centimeters, this is 0.5, which means that this is going to be equal to 0.25 centimeter only. So A is much smaller than R. R is 15 centimeters, and A is 0.25 centimeters, like 0.25 and 15 centimeters. That is, R is 60 times greater than A. Okay. So it's 60 times greater. So which means like when you square it, then what happens? It's 60 times becomes like 3600, and this is 1. A squared is 1, and R squared would be 3600, because R is equal to 60 times A. Right? It's 0.25. And this is 15 centimeters. So R squared would be equal to 3600 A squared. Okay. So like I can ignore the A in that equation. So then I can straight away use the equation for the dipole. Right. I can find the E here. So what did we find? So like E was equal to K then Q by R cube, or KP. KP R cube. So that was your E. Right? You can keep this as a dipole, because like if you think about it, this distance is much greater than this distance. So this equation should hold good. This is what we already derived. Kp by R cube. So if we just plug those numbers in, what I'm going to get now? What is K? K is, it's 2kp, right? Okay, it's 2kp by R cube around this. So this is going to give me 2 into 9 into 10 power 9 into, what is P? Can I calculate P here? So P is going to be equal to, this is 0.5 into 10, right? So 10 microcoulomb, 10 into 10 power minus 6, and what is the distance? 0.5. So into 0.5 into 10 power minus 2. That's my P. Q D, or Q into 2A. That's what I got there. Divided by, what's R? R is 15 cube, right? So 15 cube, 15 to 10 power minus 2. So 15 into 10 power minus 2, the whole cube. Right? Yeah, let's try to do this. So this is equal to, so this 2 into 0.5 will become 1. So simply I'm going to get 9 into 10 power 9 into this 10 into 10 power, this 0.5 is gone, because 2 into 0.5 is 1, 10 power minus 8, 10 power minus 8. Okay, so divided by 15 to 15 to 15 to 10 power minus 6. Right? Hope this makes sense to you. So what do you get here? 10 power minus 8, 10 power minus 6 gone, and get minus 2 here. Okay, so 10 power minus 2, and then this is 10 power 10, 10 power minus 2. So I'm going to have 9 into 10 power is 9 plus 1, 10 minus 2, so 8, 10 power 8 divided by 15 to 15 to 15. Well, if I take 3, then this is going to be 5, and I have one more 3, and I can remove this also. This will also be 5. So 25 into 15 is what I get. Okay. So this is going to give me this E value. This E value is going to give me 10 power 8 divided by 25 into 15. Okay. So let's say 25 I got here. This 10 power 6. I can write this 100 into 10 power 6, 10 power 8. Okay. So divided by 25 into 15. So kind of it's 4, right? So 4 by 15. So what can I do? If we take 40, like if we do 40 by 15 into 10 power 5, I can write this, right? So that gives me 8 5s are 40, and then 3 5s are 15. So 8 by 5 and 10 power 5. So 8 by 5, so 2 point, then 20 by 3, 6 will give me 18, 20, so 6 into 10 power 5 Newton per Coulomb. So that's me in this direction, the direction of P. I know the direction of P. So in the direction of P. So let's say P unit vector here, direction of P. Okay, so that's the first part. That's the first part. What's the second part? Second part is like you're going to take a point, like okay, along the vertical line, the same distance. This is going to be 15 centimeters. This is 15 centimeters, and this is 15 centimeters again. And we have already derived that also, right? So what is the E? This is B. Okay, what is this? I call it as E at A. So E at A, E at A, E at A. Okay. Now, what is E at B? So E at B, we know that it was simply K minus K P by RT. That's what we did. Well, this is minus K P by R cube, and this is 2K P by R cube. You see, this is twice the amount. So what would the value of this? The half of this value, simply, right? Half of this value. So the value is going to be equal to, you calculate this magnitude to be 2.66 into 10 power 5. Then what's the magnitude of this? This is going to be, the magnitude of this is going to be, say 1.33 into 10 power 5, very simply. Because it's twice that, right? You can see that. That's what we also discussed a little while ago. 1.33 into 10 power 5 Newton per Coulomb, and that's the unit anyway. Newton per Coulomb is all right. But then, which direction is this going to be? It's going to be the direction opposite to the direction of P, right? So I'm going to have P unit vector and minus. Right? This is in the P direction, and this is in the minus P direction. So that's what it means. It's the minus P direction. Okay? And Newton per Coulomb, simply. So this is your EA vector, and this is your EB vector. like this, and your EB is going to be like this. EB is like this, in this direction, and it's going to be half of EA in magnitude, but it's going to be much longer, much bigger, and like this, okay. And it will be much smaller than that. Okay. It's like it's twice this magnitude must be here, and it's in this direction, but there it's in that direction. So this is how we do the problem. You see, you can either do it like this, or you can just take these distances and then you treat them as two separate charges and find the field and add them as you've done before in the system of charges. E due to a system of charges, right? We did that. So you can do the same thing for this point and this point from the fundamentals. You will get the same value. In fact, your textbook does it both ways. It does it in the fundamental way and also compares it with this one, okay, this value. But now that we've derived this couple of equations, we started using the equations straight away. But your textbook does this problem in both the ways, from the fundamentals, which you already know how to do. Take this charge, find EA plus, take this charge, find EA minus, then add vectorially. Same way. Take this charge, find EB plus, take this charge, find EB minus, add them vectorially. Simple. So your textbook does it both ways. Then it's just to tell you that you are going to get the same results either way, approximately same results either way. So we are just skipping that part and then we are doing it using the dipole equation. Hope this is clear to you.